Hello, my name is Dr. Matthew Michael. I teach in GIT and I'm in the math department. This is the Math 222 differential equations. So preparing for different exams, I'm walking through the book's presentations of these sections so that my students and maybe others can help and learn what's going on. So in section 6.4, we're coming from 6.3, talking about the unit step function. So whereas the unit step function was useful, discontinuous, it was useful in these jump discontinuities, 6.4 is saying, look, what can I do with this? Because note, you have a jump discontinuity, a unit step up here at t is equal to 5 with a unit step down of 1 at t is equal to 20. And on the right, we can see what an effect that has, the turning on and the turning off of this unit step function. What does it mean to have a discontinuous forcing function? What does it mean for its graph? Because that's the only thing we're really changing to our solution style. Best way to start is talking about actually solving a problem. Now, last time we talked about what this g of t function would look like. It would be the u5 minus u20. Now, once again, we're dealing with the easy case, the initial condition is equal to 0. This is very doable with or without 0 initial conditions, but we're going to make it easier on ourselves by saying the initial condition is 0. 2y double prime plus y prime plus 2y is equal to g. 2 meaning if we were imagining it with springs, this would be a mass of 2 kilograms, a dampener of 1, so that's 1 Newton for every meter per second this spring is moving, whereas k is equal to 2, a spring constant of 2. This would mean that we kind of have an understanding of forcing function, that at t is equal to 5, suddenly maybe a baby is pushing up on your spring because you left them unattended, I guess. You have something pushing up with the force of 1 on the spring, always pushing up. But at t is equal to 20, you pick up the baby, or the engine's turned off, or the light is turned off, and now the forcing function isn't there anymore. What does this unit step function, this discontinuous forcing function, do to our problem? Well, take the Laplace transform of everything. We've already talked about how it works before. We have 2y double prime plus y prime plus 2y is equal to u5 minus u20. They both have a common s term in the denominator. Now, after we group the capital Y terms and the initial conditions together, we do realize, notice at the very top, that our initial conditions are 0, so these have no effect on this problem. So solving for y, we get this as a problem. We get this as a solution in Laplace space. Not in time space, we're going to need to move back, but in y space we have this. Now, as we kind of talked briefly before, sometimes it's going to be easier if whenever we see an exponential function in Laplace space, that if we can group terms of the e term together, or the away from the e. So notice we have a denominator right here. We have an h term here, all multiplying by these exponentials. Now from last time we know that the exponential means a phase shift, like we see below, along with the unit step function turning on and off. But h of s, in and of itself, I can determine by myself, by yourself. And so by doing that, we can then write it in easier to understand form. So let's find what h of t is. Well, using partial fraction decomposition, we notice an s here and an irreducible root here. We break it up into this form. Now, because irreducible means we have a linear term on top, a linear term means we have a constant on top, we just group by the terms of s in our numerators after we get rid of the denominator. The quadratics on the left are equal to the quadratics on the right. The linear on the left is equal to the linear on the right. The constants on the left are equal to the constants on the right. Now, look, the right term only has constants, no linear, no quadratic, so that's why 2a is equal to 1, or a is equal to 1/2. Since there are no linear terms on this side, this a plus c is equal to 0. So whatever a is, c must be its negative. Likewise, we solve b is equal to -1, giving us this lovely form: h of s is equal to 1/2 over s minus, because notice b and s both have negative signs, s plus 1/2 over 2s squared plus s plus 2. Now we get to the tricky part. Now, this first part is easy, but this second part should ring some bells from earlier on in this chapter talking about Laplace transforms, saying, look, I have a square term in the denominator. This means we have either a sine, a cosine, a hyperbolic sine, or hyperbolic cosine up our alley. I need to figure out which one it is. In order to do that, I need to complete the square. So I need to get rid of this 2. So notice the first step is to get rid of this 2. Then I need to complete the square by focusing in on that b term. Take this b term, 1/2 s. So 1/2 divided by 2 squared is 1/16. So subtract 1/16 from 1, and that remainder is going to be your a squared, either for the trig or the hyperbolic trig functions. Notice this is a plus here, right? So that means I'm going to be dealing with normal trig, not hyperbolic. So this is either sine or cosine functions that we're involving. Now, there is a s in the numerator. So if you remember, that means at least one of the terms that could come out of this fraction has to be a cosine. And this completed the square here tells me that an s plus 1/4 is required in the numerator to get my cosine. Because whatever happens in the denominator must match the numerator for a cosine. But that means I have an extra 1/4 hanging about. So it turns out that this isn't just a cosine, it's a cosine and a sine. Unfortunately, remember that for sine, that a squared in the denominator means I must have an a in the numerator. So this becomes one of the more undesirable aspects or more difficult aspects of the Laplace transform. If I have a 15/16 in the numerator, I have to somehow make the square root of 15/16 be in the numerator. Now, square root of 16 is easy. That's the 4. But square root of 15, that's not anywhere. So whatever I do in the numerator, I have to do in the denominator. So I have a 1/2 over s minus a 1/2 times s plus 1/4, blah, 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 minus 1/2. Also include the square root of 15 for my sine term. So when all is said and done, 1 over s is just 1. So 1/2 times 1 is 1/2. Minus 1/2, notice is an s plus 1/4, right? Not just an s squared. That's an exponential. Because remember, exponentials in real space make phase shifts in Laplace space. So we have an e to the negative t over 4 cosine, square root of 15/4t. And lastly, we have a similar sign that's being shifted by the exponential. Notice, even though this form's not particularly lovely, it's a lot better than if I had to worry about these phase shifts t minus 5 and t minus 20. Put all together, we get this as a graph. Notice, before t is equal to 5, this part of the graph is 0. This part of the graph is 0. So we start at 0 all the way to t is equal to 5. Then, take a look at t is equal to 5. So t is equal to 5, this turns on. So 5 minus 5 is 0. Plug in 0 here. 1/2 minus cosine of 0 is 0. E to the 0 is 1. So that's 1/2 minus 1/2, or 0. Sine of 0 is 0. So this literally is 0. That's why it matches up. It's still continuous here. But as t approaches infinity, cosine and sine, right here, both oscillate. Exponentials with a negative root mean that it's decaying. So it starts off at 0. But this term goes away and this term goes away. So it decays up to 1/2. it goes up and wiggles around 1/2. Then at t is equal to 20, the same thing, the same process begins again. Only now instead of adding 1/2, this subtraction sign means I subtract 1/2. So where it's centered around 1/2 here, now I'm centering around 0 here, 1/2, this 1/2. Another way I could approach it if I don't want to use Laplace transforms, I can use the same methods that I have before, is just to make it composite initial value problem, i.e. you solve the problems recursively. From 0 to 5, solve this differential equation along the top. Notice because I have 0 initial conditions, or conditions which are equal to 0, this solution will always be 0, as long as there's no forcing term. So that's why, for the second step, we still have 0 initial conditions, because y1 is 0 there. So, once again, now solve for y2. Now, because of this forcing term right here, it won't be 0. Remember this right here. Lastly, now solve along this domain from t beyond 20. Notice here I actually am using y2 because y2 is indeed non-zero because of this forcing term. So this initial condition for y3 is an ending condition for y2. And so we can go one step at a time. First from 0 to 5, then from 5 to 20, and then from 20 on. This will still match. Notice these are the same graphs. 0, look, that solution should look familiar. Notice the difference is a centering around 1/2 and a centering around 0, i.e. there's nothing here. And since we're using these methods right here, these methods of solution, because remember the 1/2 comes from this one right here. It's a forcing term, so we had a constant here. These methods still work. So if we want to avoid the Laplace transform, we do have a valid other project. It's just, do you want to solve one problem that's harder, or do you want to solve 3 that are easy? And that's a valid, preference. Some people will find one or the other easier. Something to keep in mind, remember the whole point of our process was to deal with the non-smoothness. The idea it was all jumpy and the like. But if I take a look at my solutions, they are rather smooth, i.e. they are continuous, even though the derivatives, and especially the second derivatives, start to break down a little bit more. That's why y prime might be continuous, but y double prime, the thing that we were centering our whole problem around, needs the Laplace transform because we do have jump discontinuities. So these integral transforms are allowing us to solve a problem that would normally not be possible, because even though P and Q are continuous, my forcing term is not. That's the power of the Laplace transform. Okay, let's do it again. So we have a forcing term, we have a problem. Notice y double prime plus 4y. We know that we should get solutions of sine of 2t and cosine of 2t. So these forcing terms should represent sine and cosine of 2t possibly. Well, in the complementary solution. On the other side, we should be noticing maybe some linearity. So let's take a look. Take the Laplace transform. Once again, we have 0 initial conditions, which are great, makes life easy. And we get this as our setup. Notice that t, those t's that were showing up, Laplace transform of t is 1 over s squared. Hence why we have a s squared on the bottom instead of an s. Once I divide out by my characteristic equation, s squared plus 4, it's time to once again figure out what my h of s is going to be. Remember, h of s are only functions that are being multiplied by exponentials. If part of the graph is not being multiplied by the exponential, you should do a partial fraction decomposition of just that, separately, uniquely, its own inverse Laplace transform. Notice I also leave the 1/5 out right here, or they did. I would do the same though, because that 1/5 isn't going to change any of the qualities that might show up in your HFS. It's not wrong to include it. Sometimes it's nicer than not. It's dependent on what you prefer. Remember what we were doing here with these setups. 1 over s squared plus 4. But remember, they came from the t. And t, in chapter 3, we learned when we were solving simple second order ordinary differential equations, we learned that t, or polynomials, refer to repeated root problems. Notice repeated fractions, repeated roots. Okay, do your partial fraction decomposition. A is equal to 0, B is equal to 1/4, C is equal to 0, D is equal to negative 1/4, just by grouping by terms. For B is the only constant, so B is equal to 1/4. For AS is the only linearity, so A is equal to 0. Because A and C are grouped together, that means C must be 0. Since B and D are grouped together, D must equal to negative B, or negative 1/4. Nice and easy. 1 over s squared is t, so this is going to be 1/4 t minus 1/4 over s squared plus 4. Problem here, I don't want a 1/4 on top, I want a 2. So multiply top and bottom by 2 to get your correct form. Remember what I said? We should expect sines and cosines and linear functions. There it is. So there's our graph. Notice before t is equal to 5 and t is equal to 10, we don't have any graph, because notice before 5 and 10, there is 0 on the other side within 0 initial conditions. So there's no reason for it to vibrate. But once I add my forcing term at t is equal to 5, and then turn that forcing term off at t is equal to 10, we now have some momentum, and so it will continue to vibrate because it had no damping force. So notice there's a forcing, so it's increasing in energy, and then it's turned off, and so it keeps that same energy. Once again, if you prefer, you can solve them separately and uniquely. Notice sine and cosine.